Okay, ladies and gentlemen, today we are going to do some review notes over periodic trends. So you need to take out definitely your notes, have your helper sheet out so we can take a gander at that. Also, you might want to have a periodic table because we're going to be looking at the periodic table back and forth along with this, looking at some values on that periodic table. So I would think that you would want that out also. Now let's talk a little bit about our learning target here. Our learning target for this particular lesson was to compare period and group trends of several properties. Okay, so how do things on the periodic table relate? How do these properties relate? Well, in order to accomplish this, we're going to have to do the success criteria. So this success criteria, to accomplish that learning target, we need to understand the periodic trends on the periodic table. So we're going to be taking a look at a few of these trends: atomic radius, ionization energy, electronegativity, which is almost the same. It's very, very similar to the way the electron affinity trend works. So we're going to group electronegativity and electron affinity in one group. Reactivity, and then finally, metallic character. So, we need to recognize that elements in the same group have similar properties. We also need to use the periodic table to determine the number of valence electrons. I don't know if we'll get to that valence electron one in this particular lesson. I don't have a slide for it, but we will eventually get to the valence electrons. The first one we're going to talk about is the atomic radius, the first characteristic atomic radius. And it is the size of an atom. And that is measured from the distance from the nucleus to the outermost electron. Now, let's look at our periodic table. Okay? Let's look at lithium. Let's look at lithium. Amelia, how many electrons does lithium have? It's up at the top left. 3 electrons. Excellent. Okay? How did you know it had 3 electrons? The atomic number was 3. The atomic number is the number of protons, remember? So if we have a neutral element, protons equal electrons. Now, lithium has 3 electrons. Let's look all the way down at francium, at the bottom of that row. Kira, how many electrons does francium have? 87. So does it make sense that francium would be a lot bigger than lithium? Okay. We've got a lot more shells, don't we? We've got a lot more shells. We've got a lot more orbitals. We've got a lot more electrons. Okay? So, as I switch my slide and say, let's look at some atomic radius trends. Okay? Group trend as you go down a column. Okay? As we go down a column, the atomic radius will increase. And we just said that. Lithium all the way down to francium. Now, let's look on our periodic table. Okay, look on our periodic table. Flip it over to what I call the back. Flip it over to what I call the back. And find on the key where it says atomic radius. Okay? Find on the key where it says atomic radius. Mine has a little red box, and it's the bottom number in the red box. Would we agree on that? Okay, awesome. So if I look at my atomic radius, let's start at lithium. 1.67, sodium 1.90, potassium 2.43, rubidium 2.65. Would you say they're increasing as you go down? Absolutely. Okay? So that atomic radius, this trend, is actually a value given to you on your periodic table. So as we go down a column we were talking about, once again, here's just a description of why. Electrons are filled onto orbitals. Orbitals are on energy levels. Okay? The more orbitals, the longer, or the farther away from the nucleus you will be. Okay? Therefore, it will have a bigger atomic radius. Now let's look at our period trend across the period. Okay? As we're moving left to right across the period, the atomic radius decreases. Now you ask yourself, why does the atomic radius decrease as we go across the period? Well, as we go from left to right, we are putting electrons on the same energy level. However, more protons and more electrons equal more attraction. Therefore, the more minuses are going to be attracted to the more pluses, and it's going to make that radius smaller. Okay? So by adding more protons and more electrons, it's condensing that radius a bit. Now let's look across. Okay, once again, let's look at, just say, period 3. Okay, period 3. Sodium 1.90, magnesium 1.45, aluminum 1.18, silicon 1.1. Is it decreasing as we go across the period? Yep. Okay, so when you drew your arrows on your helper sheet, you should have arrow going down. Okay, because the atomic radii increases going down a group, and you should have an arrow going from right to left, I believe. Is that how we did it? Because it is getting bigger. Okay, it is getting bigger as we go from right to left. So when I'm thinking about these, okay, based on what we have discussed here, what element should have the greatest atomic radius? Carly, what do you think? Francium. Now, if you look at the atomic radius, francium doesn't have a value, okay? Probably because francium will react pretty violently, so maybe they can't determine the radius, would be my guess. But when I'm thinking about atomic radius, I'm thinking about francium, because that's where my arrows point to being the biggest atomic radii. Okay? Ionization energy. Ionization energy is the energy that is needed to remove outermost electrons. Now, the energy, let me say that again, the energy to remove the outermost electrons. Those are what we call the valence electrons. Now, remember we talked about a group called the halogens yesterday, right? And we said those halogens were how close to filling their outermost shell? Tyler? 1 electron away. So do you think that the halogens are going to fight like heck to try to keep all of their electrons? Yeah. What about these right here, these noble gases? What do we say about their outermost energy level? Okay. What do we say about that? Carly H? I can't hear you. They're filled, right? Good. They're filled. So do you think they want to give up electrons? No. So look at these values here. Okay? Look at this value right here. The very top one, the ionization energy. What elements have the greatest ionization energy in their period? The noble gases. They don't want to remove electrons. Now, we talked about the alkali metals, right? The alkali metals have how many electrons on their valence level? Okay, Paige, what do you think? Here's the outermost energy level. Okay, here it is. How many electrons there on the outer level? If you were going to say, let's talk about, label it, like we know that the alkali metals are S's, right? So what is the first row? S what? 1. So how many electrons on their outer level? 1. Excellent. So, okay, so before we are interrupted, we said that these alkali metals have 1 electron on their outermost energy level. So do you think that they would want to get rid of that 1 electron? Okay. If you get rid of 1 electron, where do you go back to? So if I'm 11 right here, if I get rid of it, I go to 10. Is 10 a place where I want to be? Yeah, because what happens with 10? Okay. Yeah, Carly? Right. Filled outermost energy level. Okay. That's what everybody is trying to get. And I mean everybody by every element. We're going to talk about bonding. We're going to talk about bonding coming up next unit. And the whole idea with this bonding is elements want to fill their energy levels. So they're going to react with other elements to help them fill their energy levels. Okay? So these alkali metals right here, lithium, sodium, potassium, they want to get rid of electrons. So their energy needed to remove, the energy needed to remove an electron is lower. Okay? So if we look at this, just looking at, let's say, this one right here, because this is my 3rd energy level right here. So if ionization energy is the amount of energy needed to remove an electron, it's going to go up as I go across that period, isn't it? Because it's going to be harder and harder to remove electrons. All right? So let's look at the trends. Let's look at our trends. A group trend, as you go down a column, the ionization energy decreases. As you go down, the atomic size is increasing. Therefore, we're getting further and further away from the nucleus, right? As we increase, we get further and further away from the nucleus. That means that there's going to be less of an attraction between the electrons. Think about a magnet. Think about a magnet. If I've got a plus N and a minus N, and I've got them real close together, they're going to be attracted, right? If I pull them further and further apart, it's going to be easier just to grab that magnet away, right? Well, that's the same thing with these electrons and these protons. Okay, so as we go down the column, the ionization energy decreases. Okay, it's going to be easier to pull off that electron. We talked about across the period. As you go across the period, the ionization energy increases. Remember, those nonmetals, those noble gases, they don't want to lose electrons, so it's going to take a lot of energy to pull those electrons off. So basically, just like I said there, metals want to lose electrons, nonmetals do not want to lose electrons. That's going to come in handy, that generalization, when we talk about bonding. If you look right here, we are going across, once again, that third energy level. And as I look over here at my values, look at my value here for sodium. Sodium has a value of 495.8. Okay, that's the amount of energy that it would take to pull off that electron. Now look, these are ionization energies. So these 1, 2, 3, 4, 5, 6, 7, it's like pulling off electrons. Here's pulling off the first electron. Here's pulling off the second electron. Notice that sodium has no problem pulling off the first electron. But look at that jump. There's no decimal in there. So now we've got 4,562. So compared to 500, that's a pretty big number, isn't it? Okay? So sodium wants to get rid of one electron. Then it's going to take a ton of energy to get the second electron off. Why? Because its outer energy level is filled if it gets rid of one. Now look at magnesium here. Okay? Look at magnesium. Where are we at? Madison. How many electrons on the outermost energy level of magnesium? Okay, we would say that is a S what? 2. So how many electrons? 2. So does it make sense that it's not going to take much energy to take away 2 electrons, but then that third one, bam, there's the rise. Okay, there's the rise. Why? Because if you take 2 electrons off of magnesium, he has a full outermost energy level. All right. Electronegativity. Electronegativity is the tendency of an atom to attract electrons. We've been talking. Who wants to gain electrons? What type of elements want to gain electrons? Stephen, what do you think? Nonmetals. So do you think that nonmetals will have higher electronegativities? Absolutely. Absolutely. Good. They will, because they want to gain electrons to fill their shells. So when we talk about trends in electronegativity, which is really the ability, the electron affinity, the ability to attract electrons, as you go down a column, the electron affinity will decrease. Okay? Atomic size is increasing, so less attraction of electrons to the nucleus. So it will decrease the electronegativity. As you go across the period from left to right, we said that the electron affinity will increase because we will want to attract electrons. Now, if you look at your periodic table, okay, if you look at your periodic table, find the electronegativity. It should be on that back side of the periodic table, and it should be the first number, the top number on the right-hand column. So if we're looking at energy level 2, lithium has a 0.98, 1.57 for beryllium, 2.04 for boron, carbon 2.55, 3.04, nitrogen 3.44, oxygen 3.98, fluorine. Are those increasing as we go from left to right? Yes. Now look at the halogens. Go from top to bottom. Fluorine down to iodine. Okay, adenine. Let's look. 398, 316, 296. Is it decreasing as you go down? Yeah. So, what element, okay, what element, Kaylin, has the highest electronegativity? It would be fluorine. Great. It would be fluorine. Fluorine has the highest electronegativity. Fluorine wants to attract the electrons. Now, so when I'm thinking of electronegativity in my mind, I'm thinking fluorine, because fluorine's the highest. So I know how it goes across a period. I know how it goes up and down a group, just by thinking of fluorine. Now, look at the noble gases. Look at their electronegativity on your periodic table. What do you notice about that, Aiden? The noble gases. Huh? I can't hear you very good. What's the electronegativity of helium? Doesn't have one. What about neon? Doesn't have one. Argon? Doesn't have one. Why do you think that those don't have electronegativities? Okay. What do you think? Yeah. They already have all of their shells filled. Great, Carly. They have all of their shells filled. So do they need any electrons? Do they want to attract any? No. Okay? No, they do not. Reactivity. Now with reactivity, we're going to find that it's going to be a little bit different. On our help sheet, you have to have lines for metals and lines for nonmetals, don't you? Because they react different. Okay? So the reactivity is the tendency of an atom to react. Metals lose electrons when they react. So metal reactivity is based on the lowest ionization energy. And where's the lowest ionization energy? Bottom left. Okay? So low ionization energy, high reactivity. So the most reactive element is going to be francium. The most reactive metal is going to be francium, right? So you should have all your arrows pointing to francium, right? Now, didn't it make sense when we watched that video over the alkali metals? We didn't see francium, but as we went down the group from lithium to, lithium was just spinning on the top. You got the potassium down a little bit farther, and the hydrogen ignited. You saw the little flames. And then when we got to cesium, it reacted so violently that it broke the glass container, right? So did they get more reactive as we went down the group? Yes. Okay. Nonmetals are a little bit different, folks, because they gain electrons when they react. So the reactivity on nonmetals is based on electronegativity. And we said that fluorine had the highest electronegativity, correct? So fluorine is going to be where all your arrows should be pointing to on your help sheet with your electronegativity, right? Okay, good. High electronegativity, high reactivity. So it depends on the reactivity where you're at on the periodic table, whether you're dealing with metals and nonmetals, metals or nonmetals. Finally, we're going to talk a little bit about metallic character. Now, let me ask you this. What do you think's going to have a better metallic character, metals or nonmetals? Yeah. What do you think, Cody? Metals, yeah. Okay. It's right in the word, right? We don't call it non-metallic character. It's metallic character. So we're going to think, even just by looking at it, that our metals are going to have a higher metallic character. So as a group trend, okay, going up and down on our periodic table, as you go down a column, the metallic character increases. Okay? So the metallic character increases as we go down. Our periodic trend, as we go across the period, metallic character decreases. Well, it makes sense, because as we go across the period, Don't we go from metals to metalloids to nonmetals? Okay? So we would think that the metallic character would be decreasing. Okay? So that does make a little bit of sense. Now, the final thing I want to talk about here, and like I said, I don't have a slide for this. But let's talk about what we call our main group elements. Who can tell me what the main group elements are? We discussed it yesterday. Okay? What are they? Excellent. It is the s and the p orbitals. So as I'm looking at right here, energy level 2, that only has s's and p's, right? So I'm only worried about the s block and the p block when I'm talking about main group elements. Now, let's look here, because we're going to compare this periodic table with valence electrons. All right? These would be the S what? S1s. So that's one valence electron. Here's the S2, right? Two valence electrons. How many valence electrons here? Okay. Well, 1, 2, and P1. 1, 2, and 1. 1, 2, and 1. 3, right? What's 1, 2, and 2? 4. So these would have 4 valence electrons. What would the halogens have? How many valence electrons? Well, count them. Huh? 7. Yeah. So every one of these would have 7 valence electrons. What about the noble gases? 8, right? How many valence electrons would oxygen have? 6. So just by looking at what groups they are on their periodic table, we can see how many valence electrons, because we're only dealing with the main group, the S's and the P's. Okay?